In this video, we're going to be talking about work and kinetic energy, specifically the connection between those two things and how we use them to solve problems. Um, Work is going to have a definition different from what you might think of it in your everyday life. And then we are also going to talk about this thing called the work kinetic energy theorem. Energy is defined as the ability to do work, and when work is done, energy is transferred or transformed from one form to another. And those may seem a little bit circular and certainly connected ideas, but that's what we've got going on here. Work done by a constant force is the most basic form that we can talk about. And usually when we talk about the work done by a constant force, we use the basic formula of the force vector dotted into a displacement vector to give us the amount of work. That has units of newtons times meters, which come to what we call a joule. And joules of energy are certainly something you've probably encountered in chemistry before, although you may have used other units as well. This is a scalar. It has no direction. It does have positives and negatives, though, and we'll talk a little bit more about that as we go through this. Work done by a changing or variable force is a little bit more complicated to deal with, but there are a couple different methods. You can certainly say use the integral form of the work formula, which is force dotted with a displacement vector dr, which is very, very small, and add up all the bits of that. That's what's on your AP equation sheet. Or you can use a graphical method, like finding the area under the curve of a force versus displacement graph. And we're going to do a lot of this. Sometimes it's curvy like this, which is a little bit more complicated, and sometimes it's not. Sometimes it is a little bit more straightforward, where we have nice geometric shapes, kind of like what we did in kinematics. In order to calculate work, you have to answer two very important questions. First of all, which object do you care about? Just like with forces, where we have to draw a free body diagram and pick an object, you're going to be picking an object here. And then two, we need to know what force you care about. So we have these phrases of the work done on a particular object and the work done by a particular force. So when we're dealing with constant forces, we use that the initial formula, and we can do a quick example to understand how this behaves. Now, a crate is pulled 10 meters across the floor at a constant velocity. It's a pretty standard scenario. We've solved problems like this before. And specifically what we're going to look at is the work done by each of these individual forces, and then the amount of work done by the net force, which is a slightly different quantity and related to those things. So I'm going to put together a little table here that we can fill out, but all the various forces we can calculate. That's your force analysis work that you've already done. The first force we're going to calculate the work done by it is the applied force. The work done by the applied force is its 100 newtons of force multiplied by the 10 meters of displacement multiplied by the cosine of the angle between those two. All right, that's what we're going to do first. And when we do that, we end up with a situation that looks just like what we have, and we end up with a value of positive 870 joules of work. Now, we can also calculate the work done by the normal force and the force of gravity, and both of those end up being 0 joules of work, not because there's no force applied, but because the displacement is not in that direction. So we have a cosine of 90 degrees, which always gives us 0. We can then calculate the work done by the kinetic frictional force, which is going to be a negative 870 joules of work, because it is 87 newtons multiplied by 10 meters and cosine of 180 degrees. And then we can calculate the net work, which is 0 joules of work. There's two methods to approach this. You can either sum up the work done by every single force, which gives us 0 joules, or, you can talk about the amount of work done by the net force. And since this is moving at a constant velocity, the net force is 0. And therefore the net work is 0. More on that in a little bit. So we can do a couple of example problems here. A 2 kilogram block falls 5 meters. How much work does the force of gravity do on the block? Those two are in the same direction. Therefore, they're going to have a cosine of 0 degrees, which gives us 20 newtons times 5 meters, or positive 100 joules of work. We can talk about taking a jug of milk and lowering it a distance of 1 meter at constant speed. Now, how much work do you do is a question. We have the R vector pointing down. We have a normal force vector or an applied force, if you want to think of it that way. That's probably a little bit better. Pushing upward, keeping it from falling as it's being lowered down. Because you're applying a force in the opposite direction of the displacement, you are doing negative work, and that negative work serves to keep it from just free falling. Again, we'll get to some of those pieces as we go. How much work is done in net, or what is the net work done on the milk? Well, that's a little bit different. The net work is the work done by the net force. And since it's moving at constant speed, we know that the net work is zero because the net force is also zero. So let's talk about the other half of work and kinetic energy, and that is the kinetic energy. Kinetic energy is called the energy of motion. And since energy is the ability to do work, that means objects in motion should be able to do some work. An easy way to think about that is we have this vehicle. If it's moving at some velocity, it has some mass. If it were to collide into this barrier and compress the barrier, right, the spring moving the barrier, we have an object that applied a force and had a displacement of an object. So the velocity and the mass of this car, you might imagine, have something to do with how much work it can do when it collides. So to calculate the kinetic energy, we use the formula kinetic energy is equal to 1/2 mv squared. Talk more in a moment about where we get that. But if we accept that and we look at the units, it also comes out as joules, which is the unit for energy, and work, which is good because they're supposed to be interchangeable because they are both related to the amount of energy something has and the transfer of energy. So let's go from that and try to think about how kinetic energy behaves. If a 2 kilogram dog runs at 5 meters per second, its kinetic energy is 25 joules, 1/2 of 2 kilograms times 5 meters per second squared. But what happens if we double the speed while keeping the mass the same? You run twice as fast. What is the kinetic energy now? Well, because V is squared, the mass and the 1/2 stay the same, but the V squared is now 100 joules of kinetic energy. Before we move on, we want to ask the question, can K be negative? We've seen that work can be negative. It turns out that K cannot be negative because it's defined in terms of mass, which is just a positive quantity, and velocity squared, which even if you had a negative velocity or a velocity in the negative direction, squaring it would eliminate all negative signs. So this is defined from work, and we want to see how they're connected to each other. If we apply a force, and this is a familiar scenario to you, you've got a force applied on an object that's sliding across a surface. If we apply a force equal to the kinetic friction, we know that the net force on that box is zero. And therefore, because of the definition of work being force times distance in its simplest form, if we have zero net work, then we have zero net force, then we have zero net work. So does that cause the kinetic energy to increase, decrease, or stay the same? Well, we know from force analysis that no net force means no acceleration or no change in velocity. And so that means the kinetic energy will stay the same if the net work is zero. We can do another scenario. What if we push harder? So now the applied force is larger than the force of kinetic friction. Well, we can ask the same question. Is the net work on the box positive, negative, or zero? If we think about the definition of net work being net force times displacement, the net force is in the direction of the displacement, so we get positive net work. And then if we think about kinetic energy, going back to force analysis, if you have a net force to the right and it's already moving to the right, we are going to speed up. We're going to have an acceleration in that direction, and that means the kinetic energy will increase. And so if net work is positive, the delta K is also positive. Now, what if we go one step further? If we let it skid to the right, we gave it a shove, but now we let it go. Now the net force is actually to the left or in the opposite direction of motion. So is the net work on this box positive, negative, or zero? Well, in this case, it would be negative because the net force is to the left and the displacement vector is to the right. They're in opposite directions, therefore we get negative net work. So does kinetic energy increase, decrease, or stay the same? Again, jumping back to our force analysis in kinematics, if an object is moving to the right but there's a net force to the left, that is going to slow it down. It is going to decrease the kinetic energy. So the delta K is negative. So let's put this together as a summary. If the net work is zero, the change in kinetic energy is zero. In other words, if you have no net force, you do not change how fast you're moving. If your net work is positive, meaning you have a net force in the direction of motion, of displacement, then your change in kinetic energy is positive, right? Speeding up. If the net work is negative, that means that you have a net force opposite the direction of motion and displacement. You get negative change in kinetic energy, or slowing down. So the work kinetic energy theorem, in summary, says the net work is equal to the change in kinetic energy. So what does this mean for us? How do we use this? Well, let's look at this example. We have a 10 kilogram block sliding across a floor, or being pushed to slide across a floor, with some net force is 50 newtons. Now, we don't know if there's friction, applied force, what. We are just being told that the net force is 50 newtons. And if it travels 10 meters, and this is a 10 kilogram object, we can calculate the change in kinetic energy of the crate. Now, this is kind of going backwards. Net force divided by mass gives us acceleration. And the kinematics relationships allows us to find that the final velocity is 10 meters per second. If we look at the change in kinetic energy, final minus initial, we end up with 1/2 mv squared, which gives us 500 joules of change in kinetic energy. You went from 0 to 500 for a change of positive 500. Now we can do this in the work domain as well. The net work should be equal to the net force times delta R. Because they're in the same direction, that's the cosine of 0, just 1. So we end up with positive 500 joules of net work, the same as the change in kinetic energy. So the work kinetic energy theorem, work net or net work equals change in kinetic energy, is a fundamental theorem. This is how the universe behaves. It's always true, regardless of reference frame, regardless of how you measure, you will always see this work. And it's a way of thinking about what we call the conservation of energy, the idea that energy can't be created or destroyed. It can be moved around, transferred from one form to another, but it's always there. All right, how do we get here? This is a quick derivation. This is not required for you to be able to do, but it's interesting to look at. So we know that a net force causes an acceleration. So if we say that the net work equals net force times displacement, and you'll notice I'm only doing this in the x direction, one dimension for simplicity. You could derive this in an arbitrary direction using kind of vector math, but I'm not going to do that today. The net force is equal to mass times acceleration, as we have defined from Newton's second law. And using one of our kinematics equations, we can say, well, the acceleration is related to the initial and final velocity and how much displacement there is. You'll see why that makes sense. You substitute that in and you end up with net work is equal to 1/2 m times v final squared minus v initial squared, which is indeed the change in kinetic energy. So the formula for kinetic energy actually comes from the definition of net work. And then we say, oh, well, each of these quantities, that 1/2 mv squared, is the amount of energy that an object that is moving has. So once we have this formula, the work kinetic energy theorem, we can do a couple of things. We can solve new kinds of problems like this. If there is a roller coaster and a 1 kilogram ball or cart or whatever it is slides down or rolls down, rolling isn't really right, but we'll get to that later, a frictionless roller coaster, what is the final velocity at the bottom? Now, the old way would have been to draw a free body diagram, try to figure out the net force, to figure out the acceleration, and then use kinematics. The problem with that is that the net force is not constant because the angle of that ramp is changing because it's a curve, which means the acceleration is not constant and we're out of luck. So instead, what can we think about in terms of the forces that are acting and how much work they do? Well, there's a normal force and there's a force of gravity, but the normal force doesn't do any work because it is always perpendicular to the path of motion. And so only the force of gravity is doing work. And the net work that is done will give us the change in kinetic energy. Well, we know that the force of gravity times delta R times the cosine of theta should give us the change in kinetic energy. And since we start at rest, that will just give us the final kinetic energy. But there's some interesting geometry to think about here, because if you look at the delta R vector, it is exactly theta degrees away from the force of gravity. And if you take that as the hypotenuse of a triangle, right, the distance traveled, the force of gravity is pulling straight down, and the delta R vector is across this way, but the height of that triangle formed by the delta R and the flat surface would be delta R cosine theta, which means that height is actually the delta R cosine theta part of this equation, meaning we can just say, well, instead of delta R cosine theta, that's the 100 meters that it went down. And if you are paying attention, that actually would give you a result that's just like the force of gravity pulling straight down. And that's correct and kind of interesting. So 45 meters per second ends up being our speed. How easy is that? I mean, maybe not that easy yet, but we didn't have to draw a free body diagram. We did need to think about the forces, of course, but we didn't need to find vectors and vector components rather, or plug it into a kinematics formula. That means that we can use this to find out things that we couldn't do before. But there are some things that this energy analysis didn't tell us. It didn't tell us the direction of the velocity. It did not tell us how long this took. So that's the domain of kinematics. And energy can't really talk about that. So the work kinetic energy theorem and conservation of energy are two ways of saying the same thing. We'll talk more about another form of it later. But now we have multiple tools that can solve the same kinds of problems sometimes. And that ends up being an issue. Well, issue is maybe not the right word for that. It's not that it's an issue. It's that you need to make a choice. And sometimes it's obvious. There's only really one way we could solve it. And sometimes you need to pick, and one of them's easier or better than the other. So choose your luck carefully and make a decision based on an actual reason, not just because it felt good. All right. So we have this new way to solve problems that we couldn't solve before, but we can also use it to solve problems we used to solve, like this one, a car skidding to a stop. Think of it an accident investigation. We're trying to figure out, was the speed that was claimed for the initial velocity, is that actually correct? And we can go ahead and draw our free body diagram. We can figure out what the net force is here. That's kinetic friction. We have that negative there because the cosine is going to be the cosine of 180 degrees. And then we can solve for our initial speed using 1/2 mv naught squared. The m cancels out of the equation very nicely. And we end up with v naught equals the square root of 2 mu g delta x. Plug in all our values and we end up with 34 meters per second. That is faster, probably speeding in this case, than the claimed starting speed. We could also do a problem like this, a box on a ramp sliding down. It has some initial velocity. We want to know the final velocity in terms of the quantities. This is a symbolic one. But if you think about what's happening, we have the force of gravity pulling down, doing work. The displacement is L, and the angle between those is cosine theta, or is theta. So mgl cosine theta. We have our 1/2 mv final squared minus 1/2 mv initial squared. The mass cancels out. And notice I've replaced L cosine theta with that height, because L cosine theta is going to give me that particular value, because the angle theta between force of gravity down and L is the angle at the top of the ramp up there, not the normal bottom of the ramp angle. So you got to be careful about that. And that ends up with 2gh equals v final squared minus v initial squared. And if you solve that for v final, that's the exact same thing you would get from solving the kinematics free fall equation, or not free fall equation, but kinematics equation for constant acceleration, which is kind of interesting. And that's what I'm showing you right here. If you just dropped an object with an initial speed v naught, you throw it downward, by the time it goes down a distance h, it would have the same speed, because there's nothing to slow it down. Air resistance doesn't count in this case, and this was a frictionless ramp. All right, that's the work kinetic energy theorem. It's important to know, as we've said, that the combination of work and energy, which are both new concepts to us, allows us to solve a lot of problems in ways that we couldn't before. So we'll do a lot of practice with that as we go forward.